We're talking about the Extreme Universe Space Observatory, or USO. Now, this will study cosmic rays as they enter the Earth's atmosphere by recording air showers as they enter the Earth's atmosphere. And it's also referred to as GEM-USO because it will be placed on the exposed facility on the Japanese experiment module. And to tell us more about the GEM-USO experiment is Roy Young. He was the optic module lead systems engineer for this experiment. Roy, thanks for joining us, and tell us a little bit about what GEM-USO is.
Well, Lori, GEM-USO is an experiment that will study the highest energy cosmic rays by not looking up at the heavens, but looking down at the Earth's atmosphere. GEM-USO is a fairly old experiment. It was first envisioned back in the late 1990s and was going to fly, sponsored by ESA. It was going to fly on the ISS, up to the ISS on the space shuttle. After the Columbia accident, we had to redesign to fit onto the HTV, H2 transfer vehicle. We have an animation showing the deployment of USO that we can show at this time. And as you can see from this deployment, the robotic arm will reach in, pull GEM-USO out of the HTV. It will then attach it to the exposed facility. We had to collapse the instrument to fit it inside the HTV. So once it is attached, then we use an expansion mechanism to expand it. This instrument is about 15 feet long, and it's about 10 feet in diameter. So it's a fairly large experiment.
So for folks who don't know, what are cosmic rays?
Well, now, cosmic rays are not like light. Cosmic rays are actually particles. They're protons and the nucleuses of atoms. And the interesting thing about them, there's a wide spectrum of these energies for cosmic rays. Primarily the ones that we're going to be looking at are the higher energy cosmic rays called ultra high energy cosmic rays. And they're an enigma, they're a mystery. These particles are minute mass, but they are accelerated to 99.999. I won't bother because it's 21 nines, 99.219% the speed of light. And if one of them should hit you, it would have the punch of a 99-mile-an-hour fastball. And this is from a particle that you can't even see.
Nobody wants to get hit by that.
Nobody wants to get hit by that. So the physics, as we understand it, is these things slowly lose energy due to the background radiation, the 3-degree Kelvin background from the Big Bang. So they have to be, the source of these high energy cosmic rays has to be within about 100 million light years of us. The mystery is we see nothing within 100 million light years of us that can accelerate particles to this tremendous speed and give them the energies that they have. So this is the mystery. The National Science Foundation has determined or released a report back in 2003 and listed the top 11 remaining or major mysteries in physics. This is one of them. Where do these ultra-high energy cosmic rays come from? How do they get accelerated to these tremendous velocities? And this is what USO will try to explore.
Tell us how it works.
Okay. Well, first of all, the cosmic rays, we don't know what produces them, but the end result is something that we can detect as it enters the Earth's atmosphere. We have an animation of this as well, and what happens is these cosmic rays, about 20 to 30 kilometers up in the atmosphere, will hit air molecules, and as they hit these air molecules, they will, of course, collide and knock particles off. These particles will knock other particles off, and these particles will knock other particles off. And as you can see from this animation, you'll see a cosmic ray come in from the top, and as you see it entering, you'll see all these particles being almost like fireworks. And this is maybe 200 billion particles. And something you cannot see with your eye. This is primarily the ultraviolet portion of the spectrum. So you and I don't see it. It'd be almost like a meteor, but it's in the ultraviolet. So we're trying to image that. And the concerns we have, or the issue we have, is this is about equivalent to the energy from a 100-watt light bulb moving at almost the speed of light through the atmosphere. So it's a very faint object that you're trying to image.
Now, there's one other thing we were going to look at. Is that correct?
This is a model of USO. As I said, USO has had several reincarnations. This is one of the older models, but it consists of 3 lenses and a focal surface.
That's a big camera.
It's a big camera, exactly. Now, most lenses are made of glass, and they're heavy, and they're not really good for space. But the interesting thing about light is, it doesn't care how much glass is there. It only cares about when it goes from air to glass, and from glass back to air. So anything in between doesn't matter. So what if you took out all that glass in between the front and the back? Well, that's called a Fresnel lens.
This is really cool. It's like a fun house, I think.
This is a small Fresnel lens, and as you can see, it can magnify, and it gives you a really big field of view.
So what do we hope to learn from this study, Roy?
Well, cosmic rays, of course, this is a physics problem that has plagued us since they were first discovered back in the early 1900s. We want to solve this problem. Cosmic rays can cause events inside of computers. They can single event upsets. They can rewrite programs in space. So you want to shield yourself from these. You want to shield people from these. The higher energy ones, fortunately, they don't happen that often. There's one of these events per century per square kilometer. So these are extremely rare events. So there's not a lot of concern of human impact, but the lower energy ones, in particular the ones produced in our galaxy by supernova, you want to study. And in fact, on ISS, there are several experiments. The AMS, there is going to be one called Ice Cream. There is one going to be called Calais. And then with Jim Uso, you'll cover the whole spectrum of cosmic rays from the lower energy ones to the ultra high energy ones, which is what Uso will look at.
And there's one other piece of animation or video we were going to look at.
Yes,
right?
And this will be an animation showing what the cosmic ray looks like inside of Uso. Now, inside of Uso, as I said, there are these 3 lenses, and there's also a focal detector. And the focal detector is 5,000 photomultiplier tubes. And that is the place where the image is recorded and stored. And what we look for is a signal that indicates you've seen a cosmic ray. So you basically store several frames of data, and a frame of data for Uso is about 2.5 microseconds. So it's a millionth of seconds. So you store these frames until you recognize a cosmic ray. Then you save that particular piece of frame, and you download it to the ground where it can be analyzed.
Awesome. Well, when will we see this launch?
Well, we're hoping to launch in late 2017 or 2018, and ideally we'd like to be on station for 3 years, and that's the goal, to gather the statistics that we need to better understand what these ultra high energy cosmic rays are.